Welcome to this demo, showcasing how a flaw in the Kubernetes API related to image pulling can be exploited to disrupt a cluster, its effects, and how this can be mitigated in the context of FLUIDOS. While other parts of the FLUIDOS platform are designed to minimize issues from noisy neighbors, prevent unauthorized access, and ensure that the cluster is secure, other threats can still arise from unexpected sources. When a workload is deployed in a Kubernetes cluster, the container image it uses must be pulled from a container registry. This process is managed by the Container Runtime Interface CRI in Kubernetes, which communicates with the Container Runtime Containerd to pull the image. This communication is handled in an asynchronous manner, ensuring a smooth and efficient process but also making it difficult to track the status of the image pull. Indeed, a user might change idea and decide to no longer deploy the workload, while its image is still being pulled. In this case, the image pull process will continue until it is completed, even if the workload is no longer needed. This happens because Kubernetes does not try to interrupt the image pull process when a workload is deleted. However, this can be exploited by an attacker to disrupt the cluster. Either way, a malicious or accidental deletion of a workload can lead to a denial of service, as useless image pulls flood the queue and prevent new workloads from being deployed. Now, we will show you a demo outlining how this attack takes place, and how the Magi system, our solution that actively monitors pulled images and detects possible misuse of the API, works. First, to start the demo, we need to peer to nodes with LICO. In our scenario, the upper terminal shows the provider, and the lower one shows the consumer. We are sharing a namespace called Rising and ensuring it is correctly deployed in the provider's node. With this demo, we want to show that even normal behavior can generate a denial of service by instantiating applications and deleting them, possibly repeating this process multiple times. Initially, we deploy a single container from an application with a large container image. Since it has more than 1 GB, it will take some time to complete. Here, we show that the application is correctly instantiated in the provider's node since it was deployed with the namespace Rising. This has also been proven by the increasing CPU usage during the download phase of the container. We decided to delete the container since its image was too big, and the container download was not yet finished. The deletion affects Kubernetes but not the container runtime on the provider's node, blocking the instantiation of new containers. Now, we will run the same command, but both nodes now support the Magi system. In the right corner, it is possible to notice the Magi system receiving the creation and deletion commands. After the last one, it also deletes the requests in the container runtime, ensuring that the node is free again to deploy new containers. This behavior is the main objective of the Magi system, and guarantees that it is impossible to block a single node using a continuous flow of rogue requests to it. Please check our GitHub repository if you want to read more or try the Magi system. Thanks for watching this demo.